the students are working on this like kind of process of working on a large format printer for use and development within the school environment. So, there we go. So the first thing I want to talk about is the fact that this past year, what we did was we actually made a joint exploration between the Advanced Manufacturing Technologies Department and the Electronic Engineering Technologies Department. Both of those departments have specialty uses and specialty outcomes. So we kind of thought that the working of those two groups in conjunction would have a lot more lasting effect on the project than just having the Advanced Manufacturing Technologies Department work alone. Such as advanced manufacturing, we work on precision machining, we do CNC operation, programming, CAD work, 3D printing is a lot of where we focus. The students do take classes in things like PLCs and electronics, but that's not where their main focus is. Where on the other side, the Electronic Engineering Technologies Department, they actually focus on, electronics, microcircuitry, diagnostics, usage of oscilloscopes and multimeters for diagnostic purposes, fixing and reading schematics, and actually doing a lot of that work that our students don't do as much of. So they have a pretty tight schedule for they actually do this class. It's one semester, it's a 15-week course, and as you can see there, they actually only have a very tight amount of time to do this project. They have about a week to decide what they're going to work on. The last group decided they wanted to keep revising the 3D printer that we're currently working on in-house. So they have this tight schedule to work on. Then they have to actually execute and actually get to a point where they can do testing and development in that same amount of time. So it's pretty intense when you really stop and think about it. But the semester is only about 90 hours for them to do it. And for most people, that's a little over 2 work weeks that they actually have to develop and test a component. The first year we did this project, we actually did a drone. So they had about 90 hours to build a drone, design and fabricate everything, and subsequent groups have decided to take on the 3D printer. It's a pretty intense thought process when you really stop thinking about it. So we usually schedule the class on a Wednesday. So when they decide that, they need components, we have a couple days to get things in. So they're not losing that 90 hours of class time to waiting on components or waiting on some manufacturer to send them out extrusions or electronic boards or things like that. Also, if they have any questions, they have time to do research. So we say they have 90 hours. A lot of times we see that they actually spend a whole lot more time than that. Last year, actually, we had a really big snowstorm during one of the classes, and the school shut down about 1 o'clock in the afternoon. The students left the school about 8 o'clock that night from our department. We were actually kicked out of the school by the facilities manager, who came by and said, "You need to leave. We're closing the school. It actually closed 7 hours ago." And our students were like, "Do we really have to leave?" And we're like, "Yes, you have to leave." So that kind of shows you the dedication that they have to it. But they have these extremely tight schedules that they abide by. So this was the project as they saw it last year. That was revision 1 of the 3D printers. The big piece of plywood that you can see is the build plate that they're using. It's a piece of 3/4-inch ply. It's 4 feet by 4 feet, and it's covered by a piece of 1/2-inch acrylic as an actual build plate. And they decided to go with this gantry setup because they were trying to do it as cheaply as possible. So that was a big goal for them, is they wanted to stay under about a $1,300 budget, which is, again, insane because you can buy tiny printers for $1,300, let alone trying to build a 4 foot by 4 foot by 4 foot or 1,200 millimeter cube printer for about that same amount of money. So not only did they do that, but they also tried to salvage as much as possible or make whatever they needed. So on this printer, they have a lot of extrusions that they use from open build systems. They use a lot of 3D printed components that they printed off our existing mold spots. At this point, we had 3 mold spot minis and 1 CAS 6 with a more extruder. And you can see they kind of had this dual why in a way, because they want the gantry to go back and forth. And then the idea that they ran into a lot was this whole pendulum effect. When they would actually jog the machine, the whole print head would actually spin like a big pendulum. And as much as they tried to correct that, it was kind of a faulty problem that they were, added from the very beginning. So the And one big thing that I have with my students is that I say to them, if you don't complete the project like something like this, I want you to make engineering notes about what would you do in the future. So the next group that's going to take on the project, they can actually take on from there. They're not going, okay, this is what we did wrong, good luck, have fun. They actually go forward and they start to make these design decisions and do research into what would actually be fixed in the future. It's a really big issue that you can see in the world is when there's no design features for what we all want. So we decided to come up with this bigger budget with the program, and as you can see there, we have a breakdown about 3 of the companies that we use. So we use Printed Solid, we use Framing Tech, and we use McMaster-Carr. McMaster-Carr, if you're not familiar with it, is a gigantic warehouse of amazing components. And we used bronze flange nuts and actually threaded rods from them because they were able to give us the size that we needed for the project that we were going to go to. Framing Tech is a company that's up in Rhode Island. They actually are a really wonderful company. Like Open Build Systems, they sell extrusions, but their extrusions are a lot more heavy duty. They're a lot more industry focused. So if you need something like a 90 by 180 millimeter extrusion for a lathe bed, you can actually go to them and they can sell you 6 meter or longer extrusions that are ridiculous. When we first talked to the company about what we wanted, the guy asked me what we were building, and I said a large format printer. He goes, are you just trying to park an elephant on top of it? And I said, that might be a problem that we face one day, so will the system hold up? And he goes, absolutely will it hold up. So we spent a little bit of money with them. They did custom cuts for us. Whenever we can get the students to understand the cost versus time dilemma, we try to have that reinforced with them. So if you're not familiar, sometimes it's cheaper for you to sit there and make something, sometimes it's cheaper to buy. A lot of times it tends to be cheaper to buy something than to actually sit there and make it. So for them to sit there and do the cuts to get a precision when we're using not as precise hardware in our lab, it makes a lot less sense than them to be able to get the cut done by a company that specializes in that. And they may say, okay, the cut costs you $3, no big deal. We're like, thank you, because that would take our student a lot longer to do, and then go on a mill and clean up that end. So, actually, sorry about that. It's a little hard to see the screen from my point of view. So we had, like I talked about, we learned from our previous teams, and that was a really big part for us. Like we're college, so we're constantly trying to move forward. We're constantly trying to develop more things for our students. So one of the things that we learned was we needed a better controller. The first group bought a controller for about $25 off of Amazon because they burned out their initial controller, which we got for about $35 off of Amazon. So the next best thing was a controller that we could get for $25 for the first revision. That came off of Amazon. We needed a grind because they burned it out about week 13 out of 15 weeks, and they were in this mad dash now to get things done. So last year when I gave the presentation, Isaac Budman was here. If you're not familiar, he also built some large format printers, and he built some Golstein. And he said to me, he goes, you really should think about the Duet 2 Wi-Fi. And I was like, why the Duet 2? He goes, well, because we've actually been able to run NEMA 23 motors off it. It's got more robust drivers. We're like, that's a big issue that we're facing right now because we actually run NEMA 23s. So he goes, yeah, get this. So we get this board, we find out that it's way easier to program, it's way more efficient, it's way more open for us, and we find fantastic results. Within about 15-20 minutes of having it out of the box, our students were able to program it, and on the test bench, we had them spinning motors within about 15-20 minutes, which was, for us as teachers, going, okay, we're in about week 3 or 4, sorry. And they're actually spinning motors, and they're going the correct direction. And when we were talking about dual Z's and they're actually spinning at the same time, we're like, this is actually good. These are good results, right? We're excited. So we had one piece that could The other thing was that Duet makes their integrated panels, which are LCD panels, they're touchscreen, and they were fantastic. This is a picture of ours, and like, you can actually see that it's pretty much laid out exactly as you would ideally want it. We had really great results in this. We were able to go into the console mode and put in G-code commands directly. So when they were starting to do testing on like how do we home X, how do we home Y, they were able to put in those G commands to actually do that physically. Rather than having to sit there and create a program to do that, they were able to directly put it in, which is good because in conjunction with 3D printing, we teach CNC operation and manually programming. So they're very familiar with those G-code and M-code commands already, so it's kind of adapting and connecting those two worlds for them, which is also a really wonderful thing for us. So, in conjunction with that, we decided that maybe EVA 23s weren't always what we needed. So the students went to a Core XY design rather than that Gantry design as a first design improvement. Well, Core XY doesn't need giant EVA 23s. We don't need that torque anymore. So to run that gantry, we went to EVA 17s, which were very, very efficient. LDO was the company that we got on, but Printed Solid over there was our supplier. We go through Printed Solid quite a bit. They actually have been really wonderful to us. They get us stuff very quickly, and because they're based out of Delaware, we're based out of Northeast Pennsylvania, we get stuff extremely fast. Not to mention their tech support and their customer support has been absolutely fantastic for us. So, armed with some new LDO motors, we started to move on. Now, the one other big thing was we needed a more robust system. So the students decided to go to a company like Framing Tech, like I was talking about earlier. We went to 90 by 90 millimeter extrusions that were 6 meters long. Like I said, you can park an elephant on these things. You can see some of the statistics on the side there. These things are really robust. Like, we were able to just kind of like take a toy Lincoln log, clamp them together just to see what they would look like in the lab in about 5 minutes. And they came on a pallet. They were really wonderful. We were able to put them in our machinery. We run mills and lathes, industrial mills and lathes, Bridgeports. So you're able to actually see in our lab that we can actually handle equipment like this, since we output our students to companies like Lockheed Martin, General Dynamics, and AML. So this is actually the current structure of our printer. As you can see, it's a little bit more robust than the first year's development. We have a full cube 90 by 90 millimeter extrusions. The Acme rods that look tiny by comparison, they're 1 inch thick Acme rods. So those you can park an elephant on as well. In conjunction, there's 4 45 by 90 millimeter extrusions on the sides of each one. There's 2 on either side of the printed rods. And what those actually do is they have Delrin slides that go into a 3D printing component that attaches to the bed. So they help from racking in the system that the students learn from the very, very get-go. As soon as they put those Acme rods on, and they kind of tried to move the bed by themselves physically, and it racked really hard. And I was like, yeah, that's a problem, right? And they're like, yeah, how do we solve that? And we're like, let's start figuring that out. So they started to figure out how they could stabilize and create cross powers throughout the system. So you can see the front there, right there and there. Those are our XY motors. We have our EVA 23s on the bottom, plenty of clearance, and we have all of our electronics all on the side here for easy maintenance. Eventually the idea is to actually slide the machine back here, and when they originally wanted to put the electronics back there, that was even a learning experience for them. Because I said to them, you guys are going to put it back here, right? They're like, yeah. I was like, there's a workbench right there. They're like, uh-huh. I'm like, do you see a problem? They're like, well, the electronics, you can just slide the machine out every time you want to do anything with the electronics. I said, you're going to slide this giant machine out every time you want to do electronics work? They're like, yeah. I'm like, do me a favor, lean up against the machine right now. They would lean on it, like everyone. 6 people. The machine wouldn't even budge. I'm like, do you want to see how we move this thing? They're like, yeah. So we get these gigantic bars that are on wheels. They call them Johnson bars. And we lift up the machine with it, and they're like, oh, okay. So I'm like, this is a great time to learn how to put electronics in a place where you can actually do maintenance, right? So that's one of the things I would love you to take away from it, is that you can build a gigantic machine like this, make sure you can actually do maintenance on it. So speaking of maintenance, we actually started to figure out how we actually attach the electronics to it. So the board is fantastic, except for the drivers are all cooled on the bottom. So we had a big issue there. the students started to think about it, and what we did was, in Fusion 360, we kind of made a digital version of the board, and we made a digital version of all these fans, and we actually started to line everything up to figure out the flow of the air through the system. So if you actually see, like, the fan and the tip of the board are almost at the same level, and that's because the air actually goes through the bottom of the system and back out the top. So it's an intake down here and an outtake up here. Using natural convection, hot air is going to rise. So we're actually going to use that to our advantage, and we're actually going to allow the airflow to go through the system. There's a little tiny port over on this side that allows all the wiring to actually be bundled and come through the system and go out, and actually not interfere or create interference patterns with the airflow. By being able to use our TAS6, we're able to 3D print this all as one component. The top is one component with an integrated reset button and a touch screen, so they can actually access the printer very smoothly and nicely. Teaching the students how to properly lay out electronics is a very big part of our educational system, because they're actually going to go out into the industry and hopefully take these kinds of lessons with them. The other thing that we started to do was development of our own custom hot end. So the students like the idea of making things themselves. The program that I teach actually has its roots in a precision machining program. So for them, they always want to make parts and parts and parts and parts. So one of the things that we try and teach them is proper part construction. So they wanted to do a direct drive because a Bowden tube on a system like this would be kind of ridiculous. And then also trying to control a Bowden tube that's 8-10 feet long and had some kind of spring mechanism and all sorts of other issues to actually be able to control that would be a little unwieldy. So we decided to go with a direct drive system. So we have the extruder right there, and then we have the drive system right there, and then we have an extruder system right here. They took apart an E3D hot end that we had, and they decided that they didn't like the fact that the hot end at the time only had a small heater block. So they manufactured their own heater block and their own nozzle from scratch, including manufacturing their own heat break out of pure titanium that they machine on the lathes themselves. And they actually developed a 2mm extrusion nozzle, and that block's about 1 inch by 2 inches. You can tell its size when you compare it to the BL Touch that's actually on there. And we had to use 2 kind of blower fans to create intense part cooling. This printer is designed to go very fast and print very large. They don't want to print thin layers. We've got smaller printers for that. So they were like, let's print big. We have other companies around us like Steamtown National Historic Park, and they build locomotives and marine condition locomotives. So it's kind of one of the outputs of this, is that they want to be able to print parts that they can use for welding over in Steamtown. So we need to be able to print very large very quickly, with very strong parts that can then be going into this kind of system. So yeah, it's actually a very big improvement over what we did last year. We're going to continue the project. One of the big issues that we dealt with was thrust issues inside of the motors, so that by putting the motors down here, they actually have all the weight centralized on these 2 points. So they've actually put a ton of thrust load on these 2 tiny motors. So one of the big ideas from the very get-go is to take these 2 motors and literally flip the Z around, and that would actually eliminate all the thrust issue right there. So that's one of the things. And then we're also talking about taking out the core XY and going to a more traditional XY system. Yeah, your eyes just perked up. You're like, oh, why get rid of it? So one of the things that we found that as an issue, and maybe it's just our programming right now, is that our belts are so long that they sag quite a bit. We're having trouble actually getting enough tension on them that the motors can actually handle that kind of tension. Even going to a stiff belt that we have with Kevlar reinforced belts on here, which are actually relatively stiff, they still sag quite a bit from one point to another. I'd say from that 4-foot distance, they're probably sagging about 1/4 inch. So what happens is the motor starts going, and the belt's moving, but it's not quite moving yet, so the tension's not quite there. So we can actually put it to a lot more tension if it's just going back and forth in that 4 feet rather than going around here, around the back, and around into the center. So we're kind of trying to deal with some of those issues. So that's something that this year's group is going to have to deal with. Is like, how do they take some of these improvements? What is nice though is that this last year's group actually left them in a really good spot to move forward. So yeah, does anybody have any questions? Sorry, what? Framing tech? Framing, yeah. So right there. Framing tech. They also give educational discounts, and they were a really wonderful company to work with. They did all of our extrusions, they did our mounting plates, our feet, everything actually. Quite a bit. It almost came together like a Richter set at that point. So like even these gigantic plates, they did those, and it came with all the mounting hardware, 10mm T-slots. It was a beautiful way to get together. The only issue we had was actually doing the tapping for it. We ended up making our own tap in-house because we couldn't get a 1/2" by 13 tap that was long enough. So we actually ended up making a 1 foot 1/2" by 13 tap to be able to do some of the work that we were doing on the system.